Good morning, viewer. Beyond this here. Here's breaking news. In an amazing phenomenon of quantum physics known as tunneling, particles appear to move faster than the speed of light. However, physicists from Darmstadt believe that the time it takes for particles to tunnel has been measured incorrectly until now. They propose a new method to stop the speed of quantum particles. In classical physics, there are hard rules that cannot be circumvented. For example, if a rolling ball does not have enough energy, it will not get over a hill but will turn around before reaching the top and reverse its direction. In quantum physics, this principle is not quite so strict. A particle may pass a barrier even if it does not have enough energy to go over it. It acts as if it is slipping through a tunnel, which is why the phenomenon is also known as quantum tunneling. What sounds magical and tangible technical applications, for example, in flash memory drives. In the past, experiments in which particles tunneled faster than light drew some attention. After all, Einstein's theory of relativity prohibits faster than light velocities. The question is therefore whether the time required for tunneling was stopped correctly in these experiments. Physicist Patrick Skach and Anno Gies from TU Darmstadt follow a new approach to define time for a tunneling particle. They have now proposed a new method of measuring this time. In their experiment, they measured it in a way that they believe is better suited to the quantum nature of tunneling. They have published the design of their experiment in the renowned journal Science of Advances. According to quantum physics, small particles such as atom or light particles have a dual nature. Depending on the experiment, they behave like particles or like waves. Quantum tunneling highlights the wave nature of particles. A wave packet rolls towards the barrier, comparable to surge of water. The height of the wave indicates the probability with which the principal and particle would materialize at this location if its position were measured. If the wave packet hits an energy barrier, part of it is reflected. But however, a small portion penetrates the barrier and there is a small probability that the particle will appear on the other side of the barrier. Previous experiments observed that a light particle has traveled a longer distance after tunneling than one that had a free path. It would therefore have traveled faster than the light. However, the researchers had to define the location of the particle after its passage. They choose the highest point of its wave packet. But the particle does not follow a path in the classical sense. Objects in a glaze. It is impossible to say exactly where the particle is at a particular time. This makes it difficult to make statement about the time required to get from A to B. Skach and Gies, on the other hand, are guided by a quote from Albert Einstein, "Time is what you read of a clock." They suggest using the tunneling particles itself as a clock. A second particle that does not tunnel serves as reference. By comparing these two natural clocks, it is possible to determine whether time elapses slower, faster, or equally fast during quantum tunneling. The wave nature of particles facilitates this approach. The oscillation of waves is similar to the oscillation of a clock. Specifically, Skach and Gies propose using atoms as clocks. The energy levels of atoms oscillate at certain frequencies after addressing an atom with a laser pulse. Its levels initially oscillate synchronized. The atomic clock is started. During tunneling, however, the rhythm shifts slightly. A second laser pulse causes the two internal waves of the atom to interfere. Detecting the interference makes it possible to measure how far apart the two waves of the energy levels are, which in return is a precise measure of the elapsed time. Beyond this exclusive report.